Rational functions are the ratios of two polynomials, so f of x is equal to a of x over b of x. When wanting to graph a rational function, you should always factor first. Factor the numerator and the denominator. Doing so, you can find things called discontinuities. There are three types of discontinuities. There's a jump discontinuity, an infinite one, and there's also a removable one. To start off, let's take a closer look at a jump discontinuity. Jump discontinuities are often found in piecewise functions. Piecewise functions look typically like this. It has a function like this. This can go on continuously, then it stops here, and then it starts down here, something like this. And as you can see, it jumps from this point to this point, and this is known as a jump discontinuity. Next, we have infinite discontinuities. These are also known as vertical asymptotes, or VA for short. Let's say we have a graph like this, then we have a function like this. However, we also have a line going like this, straight down the middle vertically. This graph is never going to reach this line, but it will approach it. So this is known as a vertical asymptote. It will never reach it, but it would approach it. The last type of discontinuity is called a removable discontinuity. Essentially, it is known as a hole. Let's draw a graph here, and we have a function going like this, except there's a hole right here at this x value. What this means is that at this x value right here, the y value is undefined, and this makes a hole in the function. To find these three types of discontinuities, remember to always factor first. This is a major part in finding these discontinuities. For jump discontinuities, normally they appear in piecewise functions. For infinite discontinuities, in order to find which x value that a vertical asymptote appears on, you can set the denominator equal to 0. So let's say we have the rational function a of x over b of x. You're going to want to set b of x equal to 0 and then solve for x. Those x values are going to be where your infinite or vertical asymptote is. For a removable discontinuity, you should always factor, and then you see which terms are like terms between the numerator and the denominator. So let's say we have f of x is equal to x minus 3 times x minus 2 over x minus 3. You can see how x minus 3 and x minus 3 appear on both the numerator and the denominator. So that means you can cross these out, and you will know that there will be a hole at x equals 3. Then once you get rid of this, your new function will be x minus 2. You can plug 3 back into here, and you can find the y value of the hole at f of x, or f of 3 is equal to 1. So that means that the hole is at 3, 1. And that's how you find the three types of discontinuities. Like I said previously, an asymptote is a line that the curve will always approach but never reach. There are two types of asymptotes, a vertical one, or the infinite discontinuity, and a horizontal one. Like their name suggests, the vertical one is a vertical line, while the horizontal one is a horizontal line. The curve will always approach these lines, but never actually touch the lines themselves. When finding horizontal asymptotes, you should always compare the degrees of the leading coefficients of the numerator and the denominator. So let's say we have f of x is equal to a of x divided by b of x. And then let's say that the numerator has a leading degree of n, and the denominator has a leading degree of m. And if n is less than m, there is a horizontal asymptote at y equals 0. If n is equal to m, there is a horizontal asymptote when you divide the leading coefficients. And then if n is greater than m, there is no horizontal asymptote, but there is something called an oblique asymptote. So oblique. To find this asymptote, you have to divide a of x over b of x using long division or synthetic division, and then you set that result equal to y. So y equals division. Another important thing to know about rational functions are their x-intercepts and their y-intercepts. To find each of these, let's say you have f of x is equal to a of x over b of x. To find the x-intercepts, you set a of x equal to 0 and then you solve for x. To find the y-intercepts, you look at each of the x's within your function and then you set all of those equal to 0. So a of 0 over b of 0. Then you find what y is, and that'll tell you where to find your y-intercepts. Now, let's combine all of this together and find the properties of a rational function. F of x is equal to x squared plus 2x minus 15 divided by x squared plus 4x minus 21. The first thing to do is always factor. So let's first factor the numerator. Minus 15. 15 you can break into 5 and 3. So x squared plus 5x minus 3x minus 15. You can factor out an x on these two terms, and then you factor out a negative 3 on these two terms. Then you combine, and this is what it looks like in factored form. Now let's do the denominator. X squared plus 4x minus 21. 21 can be broken into 7 and 3. So x squared plus 7x minus 3x minus 21. You factor out an x from these two terms, then a negative 3 from these two terms. Then you combine. X minus 3 times x plus 7. And these are the factored forms of the numerator and the denominator. Now we can rewrite the function as x minus 3 times x plus 5 divided by x minus 3 times x plus 7. First, you find discontinuities. You can see how the x minus 3 factor appears in both the numerator and the denominator. So you can cross those out, and you can know that is a whole. So x equals 3 is where a whole appears. So let's rewrite the function as x plus 5 over x plus 7. You plug this 3 back into your new function, and you would get 3 plus 5 over 3 plus 7. This is 8 over 10, or 4 over 5. This means that there is a whole at 3, 4, 5. Now that we have our new function, we can find the other discontinuities. Since this is not a piecewise function, there are no jump discontinuities. However, there is an infinite one. So to find the infinite one, you set the denominator equal to 0, and then you solve for 0. This means that there is a vertical asymptote at x equals negative 7. So we can write there is a vertical asymptote, x equals negative 7. Now we have to find the horizontal asymptotes. Knowing from before, if n is less than m, you will have a horizontal asymptote at y equals 0. If n equals m, you will have a horizontal asymptote by dividing the leading coefficients. And then if n is greater than m, you won't have a horizontal asymptote, and instead you'll have an oblique asymptote by dividing the polynomials. So now let's look at our function x to the power of 1, x to the power of 1 with coefficients of 1 and 1. This will mean that n is equal to m, so you divide the coefficients. And this means that there is a horizontal asymptote at y equals 1. So we can write this up here, HA with y equal to 1. Now we have to find the intercepts of this function. Let's first find the x-intercepts, and you do so by setting the numerator equal to 0. So x plus 5 equals 0. This will mean that x is equal to negative 5. So there will be an x-intercept at negative 5, 0. Next, you can find the y-intercepts. You do so by setting all of these x's and replacing them with zeros. So 0 plus 5, 0 plus 7. And this is 5 over 7. So this will mean that there is a y-intercept at 0, 5 divided by 7. Now that we know everything about this rational function, we can finally graph it. So first, let's graph what we know. 3, 4 over 5 is where the whole is located. X equals negative 7 is where the vertical asymptote is. Y equals 1 is the horizontal asymptote. -5 comma 0 is the x-intercept, and then 0 comma 5 over 7 is the y-intercept. Now let's graph the actual function. F of x is equal to x squared plus 2x minus 15 divided by x squared plus 4x minus 21. Now let's take a look at what this looks like. And as you can see, this graph perfectly fits within the asymptotes. This one and these and this one. As you can see, the graph continuously approaches the asymptotes but never actually touches them. And look at the x-intercept and the y-intercept. The graph perfectly crosses through the intercepts at these points, and then this is where the hole is. If I hide this and I go to this point of the graph, you can see how it says 3 comma undefined. This means that there is a hole at this graph, which also means that our answers were correct.